In this video, we're going to go through titrations. So in a titration, you have an analyte, which is a chemical that you're not sure of the concentration on. So you're going to be analyzing the analyte, hence the name. And then you have a titrant. A titrant is a chemical substance where you know the concentration. So you have a substance where you have an unknown concentration that you're trying to figure out, and then you have a substance with a known concentration that you're going to use to determine the concentration of the analyte. All right, there are three types of titrations. There's an acid-base titration, and in an acid-base titration, we are trying to find the point where the pH changes. We have a redox titration, that's an oxidation reduction reaction, and we're trying to find the point where the oxidation state changes. And then finally we have a precipitation titration, and in this titration the titrant reacts with ions in the analyte and a precipitation or a solid occurs. And the precipitate or color change indicates our endpoint. Okay, so we have 2 points. We have the equivalence point of the titration, and that occurs when the analyte is totally consumed by the reactant species in the titrant. So, for example, our equivalence point in an acid-base titration, the number of moles of hydroxide ions will equal the number of moles of hydrogen ions. So the concentrations are equal. The endpoint is when the indicator changes color. So your equivalence point and your endpoint aren't necessarily the same point. So in an acid-base titration, indicators are all weak acids, and our color changes occur at different pH ranges. So it's not necessarily 7. Our endpoint could be at a variety of pH levels. It depends what you're looking for. So here is the setup for an acid-base titration. And we use the same setup for all of our titrations, but in this case we're looking specifically at pH, so this is an acid-base titration. So our setup uses a burette. Our burette holds our titrant, which in this case is sodium hydroxide, our base. In our Erlenmeyer flask down below, we have our analyte, which is an unknown concentration of hydrochloric acid. Now, because it's an acid, we're going to be starting with a low pH. As I add base to the acid, my pH begins to climb. Now, eventually, we're going to reach a pH of 7, and that's the point where our indicator will change color. So when we're doing an acid-base titration and we're using phenolphthalein, it's going to turn this pale pink color. Okay. So that pale pink color is what we want. Now if we continue to add base, the pH will continue to climb, and eventually it'll reach a really high pH, indicating that our solution is basic, but that's not what we want. We want to stop it right when our pH is 7, when our phenolphthalein causes the solution to change that pale pink color. All right, that's a titration in a nutshell. So let's look at some problems here. So our first problem says 10 milliliters of hydrochloric acid was put into a flask using a volumetric pipette. 25 milliliters of H2O were added to the flask, as well as 3 drops in the indicator. 0.4 molar sodium hydroxide was put into the burette, and the initial volume was 0.51 milliliters. The sodium hydroxide was added to the flask until a pale pink color lingered for 30 seconds. The final volume was read at 18.5 milliliters. Find the concentration of the hydrochloric acid. So we want to get the amount of our base that we used, because we were starting with 0.51 milliliters, and at the end we had 18.5 milliliters. So we want to figure out how much of our base was dispensed. So we're going to do final minus initial to get that amount. So our ending amount was 18.5 milliliters, and our starting amount was 0.51 milliliters. So if I subtract those on my handy dandy calculator, let's see, 18.5 minus 0.51, I get 17.99. All right, now of course we can't do everything in milliliters, so we have to convert it to liters. So to do that, we're going to take our 17.99 milliliters and we're going to set it up in a conversion. So there are 1,000 milliliters in 1 liter. So when I do that conversion, I get 0.01799 liters. All right, but that's not what we were trying to solve for in this question. In this question, we're trying to figure out our concentration of our acid. So we know the volume of our base. We need to figure out the, first of all, moles of our base. Then we're going to do a mole ratio to go from base to acid. And then we'll need to convert our moles of acid into our concentration or our molarity of our acid. Okay, so let's start with our liters. So we have 0.01799 liters of base, which is NaOH. And we're going to need 3 steps here. The first step, we're going to convert it to moles. Second step, we're going to convert it to acid. And then our final step will be to take our moles of acid and turn it back into molarity. All right, now looking at the question, it does tell us our molarity of our NaOH. And remember, molarity is moles over liters. Okay, so if I know the moles over liters, that is going to be our conversion factor for our moles. So if it's 0.4 molar, that means that I have 0.4 moles in 1 liter. And these are moles of NaOH. Okay, now the ratio of NaOH to HCl is 1:1. So for every 1 mole of NaOH, I have 1 mole of HCl. So 1 mole of NaOH. And then we have 1 mole HCl. HCl. Okay, great. Now, we don't know the concentration of our acid. So we're not going to be using the same moles over liters to convert this back. But we do know the volume of our acid that we used. We know that we had 10 milliliters in our Erlenmeyer flask when we were doing the titration. Of course, we want to convert that to liters. So 10 milliliters divided by 1,000 milliliters gets us 0.1 liters of acid. 0.01 liters of acid. Now there's nothing that's going to go on the top here of our fractions. I'm just going to put a 1. Okay, so let's do the math here. So 0.01799 times 0.4 over 1. So I'm just going to multiply that by 0.4. Okay, times 1 over 1 will just be the same number. Times 1 over 0.01. So I'm going to divide that by 0.01, and there's my concentration. So all of our sig figs, it looks like, let's see, we have 3. That is our smallest amount, so 0.720 molar will be the concentration of our acid. All right, let's do another one. So in this question, we have a 0.35 molar solution of sodium hydroxide. It's reacted with 25 milliliters of an unknown molarity of sulfuric acid. It takes 7.3 milliliters of sodium hydroxide to react completely with sulfuric acid. Determine the molarity of the acid. So just like the last one, let's take a look at the information that we have. So we have the concentration of our sodium hydroxide. We have the amount of sodium hydroxide, so we don't have to determine this like we did up here. It's given to us in the question, and we know how much of our acid is left, or rather, how much of our acid was in our Erlenmeyer flask. All right, so we're going to start with our volume of our base. So 17.3, divide that by 1,000, I get 0.0173 liters of our NaOH. Okay, just like the last one, I'm going to need 3 steps here to figure this out. So step number 1, we're going to use the molarity of our base to determine the number of moles. So 0.35 molar, again, just like we did in the last one, moles over liters. So there are 0.35 moles in 1 liter. That's moles of NaOH. Okay. There are 2 moles of NaOH for every 1 mole of our acid. So 2 moles of NaOH for every 1 mole of our H2SO4. Okay, and then just like in the last question, to get our concentration, we're going to use the amount of acid. So it was 25 milliliters, so 0.025 liters of H2SO4. And then I'm just going to put a 1 on the top here. Okay, so let's do the math. So 0.0173 times 0.35 over 1, so just times 0.35, times 1 over 2, so I'm just going to divide by 2, and then times 1 over 0.025, so I will just divide that by 0.025. All right, so our answer, and again, looks like 3 sig figs is our number, so 0.121 molar is going to be our answer. All right, one left. Determine the molarity of an unknown HCl solution if it takes 20 milliliters of 0.75 molar sodium hydroxide to react completely with 10 milliliters of the HCl. So we have our concentration of our sodium hydroxide, we have the amount of sodium hydroxide, and then we have the amount of our acid. So let's start with our volume. So we need to convert this to liters. So 20 divided by 1,000 will get us 0.02 liters of NaOH. We're going to need 3 steps just like we did in the last one. Okay, so our concentration is 0.75, so that means there are 0.75 moles of NaOH in 1 liter of NaOH. 1 to 1 this time, so 1 mole NaOH for every 1 mole of HCl. All right, and then finally, we know that we have 10 milliliters of HCl. Converting that into liters, then of course we put our 1 on the top. So 0.02 times 0.75 over 1, so times 0.75 times 1 over 1 will get us the same number, times 1 over 0.01, so divided by 0.01, 1.5 molar. All right, that's titrations.